So let's take a look at using truth tables to establish certain logical equivalences. We're going to start with a double negation. Specifically, any statement P is logically equivalent to itself negated twice. Well, we need to construct a truth table for a biconditional statement. It has only got one literal in it, so I just need those two rows. Now, fundamentally, I need to construct the biconditional statement, P if and only if it's double negation. Before I can build this biconditional arrow, I need not P, but before I can construct not P, I need not P. Now the negations are pretty easy to work out, where P is true, not P is false, but if not P is false, not P is true. Where P is false, not P is true. If not P is true, not that is false. And now I can ask, are these two columns the same? Well, yes, in this row, I have true and true, and in this row I have false and false. So those two columns were the same, always, which means the biconditional arrow is always true. In other words, it's a tautology. And if two statements with a biconditional arrow between them is a tautology, those two statements are logically equivalent. A collection of other logical equivalences are known as commutative properties. Specifically, here they are. P and Q is equivalent to Q and P. P or Q is equivalent to Q or P. We're going to do one of these, but not both. Now, no matter which one we did, there would be two literals involved. I would need to form a biconditional arrow, and the two literals are P and Q, so I need 4 rows. Let's suppose we're going to build up this second one, that the disjunction symbol is commutative. I can swap right and left and remain logically equivalent. Then I need to build up this biconditional arrow, which means I need each of these two things as their own columns. Those both depend just on P and Q. Now this column is just copied out of the truth table for P or Q. Is one of them true? Yes. Is one of them true? Yes. Is one of them true? Yes. Are both true? No. Now this column is not exactly a copy of this. We simply ask the same question. Is Q true or is P true? Yes, they both are. Yes, P was true. Yes, Q was true. No, they were both false. So there's that column. And finally, we can ask, is this column the same as this one? And here those two are, and observe that, yeah, they're always the same. It's not that they're always true or always false, but they are always the same. So this biconditional arrow is always true, which means the biconditional arrow is a tautology. And when two statements joined with a biconditional arrow form a tautology, those two statements are logically equivalent. And so there we have this one for disjunction. There's also a collection of logical equivalences known as associative properties. Okay, there's one for a conjunction with another conjunction, and there's one for a disjunction with another disjunction. If I have 3 statements P, Q, and R, and I want to conjoin them, I could conjoin the latter two and then tag on the first one, or I could conjoin the first two and then tag on the third, but it won't make a difference. This is, as a collection, is true in exactly the same scenario where this is, and similarly for false. And then there's one for disjunction. Notice, however, that I am not mixing conjunctions and disjunctions. I have 3 statements with 2 conjunctions, or 2 disjunctions, 2 disjunctions. I do not have a statement that has both a conjunction and a disjunction in it. Well, as before, we're really only going to do one of them, and it doesn't matter which one. There's 3 literals, so I need 8 rows, and here they are. Let's suppose, unlike last time, we're going to do the version for conjunctions. So we need to show this, if and only if this is a tautology. So there it is. We want this to all be trues. Before I can build up this statement, I need this as a column and P and Q and R. So I'm going to need to build up P and Q and R, but before I can do that, I need P and Q. I also need P and Q and R, but before I can do that, I need Q and R. All right, so let's start filling in the truth table. Q and R is just a matter of looking at these two things. Both true, yes. No, 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 not both true. So true, otherwise falses. Now I just need to form a conjunction with P, the first column, and the one we just made. True, true, makes true. True, false, false. True, false, false. True, false, false. These last 4 rows, since P is false, this conjunction is definitely going to be false. Okay, moving on. We do basically the same thing. Let's compare P and Q. Well, in these two rows, they're both true. In all the other rows, at least one of them is false. Now I'm going to form a conjunction with the column we just made and R. True, true makes true. However, every other row R is false, so every other row this conjunction is false. And once we pass the second row, P and Q is false, and therefore these are all false as well. And finally, we can ask, this column and this column, are they the same? Yes, in every row, they're the same. There's only one row in which they're both true. In the rest, they're both false, but it was always the case that they are the same as one another. So these two statements are logically equivalent because the biconditional arrow is a tautology. Are they always the same as one another? Yes. Okay, and if two statements are always the same, not necessarily always true or always false, but always the same as one another, that's logically equivalent. There's a very similar way to do this one for disjunctions. Okay, there's also a collection of logical equivalences known as distributive properties, and these have to do with what happens when you actually mix one symbol with another. And there's a bunch of them. Okay, what happens if you have a disjunction that has a conjunction versus a conjunction with a disjunction, a conditional statement with a conjunction, a conditional statement with a disjunction, both of these being in the conclusion, or a disjunction versus conjunction in the hypothesis? And there's a certain way of expressing all of them, which is logically equivalent. Of course, we're not going to go through and do every single one of them manually, but we will do one of them. All right, here it is. Okay. We have chosen the first one, that P or Q and R is logically equivalent to P or Q and P or R. That's this first line here. So I need a biconditional arrow. So first I need this to be built up. That's why it occurs to the left. I also need this, and that's why it's over here to the left. Before I can have P or Q and P or R, I need both P or Q and P or R. And before I can do P or Q and R, I need Q and R. So you can double check that everything checks out here. Here are my 8 rows. If I just focus on Q and R, I can get this column here. There are only 2 rows in which both Q and R are true. Now I can disjoin it with the one I just made. Either P is true, which is definitely the case in the top 4, or perhaps Q and R is true, which is also true here. Otherwise, both P and Q and R were false. So here's the column for this statement, P and or Q and R. Then I can build the disjunctions individually, P or Q, P or R, and then I can conjoin them. And then I can compare these 2 columns that I made, and you'll find, yes, they are always the same. So these 2 statements are logically equivalent. Okay, all of the other distributive properties can be shown through a truth table. We're not going to take the inordinate amount of time it would take, but I highly recommend that you do by hand 2 or 3 of them at a bare minimum. It's excellent practice in making truth tables. Also, you know what the end result is supposed to be, which can help you catch errors. Okay, there are some other important ones called De Morgan's laws. De Morgan's laws has to do with how a negation distributes across either a conjunction or a disjunction. Notice that a negated conjunction becomes a disjunction of 2 negations. A negated disjunction is a conjunction of 2 negations. And we're only going to do one of them. Either way, there are 2 literals, P and Q, so we need 4 rows. Let's suppose we're going to go ahead and do the first one. The negation of P and Q is equivalent to not P or not Q. Well, before I can build this biconditional, I need its right side, which involves needing both not P, but also not Q. I also need the negation of P and Q, but before I can do that, I need P and Q. And now we can start filling it in. So first up, the conjunction is only true in the row where both P and Q are true, but then I exactly flip that. So here is my negation of P and Q. Then I can build the negation of P, the negation of Q, and I can disjoin those. So this is just the reversal of P, and this is reversing Q. And then I asked, was either one of those true? Nope. Yes, yes, and then here they both were. And now I can compare, is this column the same as this one? Both false, both true, both true, both true. So the biconditional arrow is always true, aka a tautology. In other words, the 2 statements were logically equivalent. And a very similar truth table will do this second one. And again, I recommend that you do this as practice. And there's a host of logical equivalences that have to do with conditional statements, but also a few things that are not logically equivalent. This strike mark through the equivalence sign that we see on the right side here just means not logically equivalent. For two statements to not be logically equivalent just means that the biconditional arrow is not a tautology. It doesn't mean it's a contradiction. The biconditional arrow doesn't have to always be false. It just can't always be true. Okay, but these are logical equivalences here. Now, we've done enough proving of things that are logical equivalences, but I do recommend, again, you check these. This last one especially is quite important. We'll revisit it. But let's actually show that two statements are not logically equivalent. Well, it doesn't matter which one we pick. We need the literals P and Q. But let's go ahead and take that first one. I want to show that the negation of P implies Q is not equivalent. In other words, not really the same as P implies not Q. So I'm going to look at this biconditional arrow, which means I need P implies not Q, which means I need not Q. I also need the negation of P implies Q, which means I need P implies Q. And now we can start filling this in. Well, here's our conditional arrow based on hypothesis P and conditional Q, which I then negate. Now I can also just negate Q and then do this conditional arrow based on hypothesis P and conclusion not Q. And then I can ask, are these two columns the same? They happen to be the same a few times. There's a typo here, I apologize. Okay, they're not the same here. But they're not always the same. Okay, notice this is not a tautology because sometimes it's false. It's not a contradiction either because sometimes it's true. But because this biconditional arrow was not a tautology, we conclude that these two statements are not logically equivalent.